Below is a clean, organized, essay-style manuscript based on the transcript you provided. I shaped it into a professional, readable piece with clear sections and logical flow. The tone stays steady and thoughtful, while the content remains accessible for students and general audiences. Newton and Einstein, a comparative essay on scientific genius. Introduction. Across the wide landscape of scientific history, two towering figures stand like twin mountains shaping our understanding of nature: Sir Isaac Newton and Albert Einstein. Each lived in a different century, worked with different tools, and faced different intellectual challenges. Yet, both revolutionized the way humanity sees the universe. Their brilliance invites a question that scholars still ponder: which genius surpassed the other in scientific insight and influence? Rather than offering a simple verdict, it is wiser to examine how each contributed uniquely to the unfolding story of modern science. Isaac Newton, the architect of classical physics. Early life and education. Isaac Newton was born on Christmas Day, December 25, 1642, in Lincolnshire, England. At the King's School in Grantham, he learned Latin, ancient Greek, and mathematics. Teachers quickly noticed that his abilities outpaced the curriculum, and by the time he entered Cambridge University, Newton was already forming his own private notebook of ideas titled Quaestiones Quaedam Philosophicae, Certain Philosophical Questions. This secret notebook became the seedbed of a scientific revolution. Scientific breakthroughs. Newton's contributions were vast. 1. Universal gravitation. Though popular culture imagines an apple striking Newton on the head, the deeper truth is that observing an apple fall led him to ponder why all objects move toward Earth. This meditation matured into the law of universal gravitation. 2. Principia Mathematica, 1687. His masterpiece, Philosophiae Naturalis Principia Mathematica, remains one of the most influential books in scientific history. In it, Newton articulated the three laws of motion, the mathematical structure of classical mechanics, the concept of a universal, predictable, orderly cosmos. 3. Optics. Newton studied light and color, discovering that white light is composed of a spectrum. Nearly every modern astronomical observatory still uses variations of his telescope design. Newton's achievements built the foundation upon which centuries of science would stand. 2. Albert Einstein, the architect of modern physics. Early life and struggle. Albert Einstein was born in 1879 in Württemberg, Germany. As a child, he was fascinated by the mysterious certainty of a compass needle and the beauty of geometry. Contrary to popular myth, he was not a poor student. He excelled in mathematics and physics, but struggled in subjects like French and biology. By 1902, however, Einstein reached a low point. He had no job, no money, and was not allowed to marry the woman he loved. His father's business had collapsed. Eventually, he secured a position as a patent clerk in Bern, Switzerland. There, reviewing inventions each day, he developed the habit of thinking deeply and imaginatively about physical problems. The Miracle Year, 1905. While working as a clerk, Einstein asked himself a strange question. What would happen if I ran alongside a beam of light? This thought experiment became the gateway to new physics. In 1905, Einstein published 4 papers that transformed science. 1. Special relativity. The speed of light remains constant for all observers, contradicting Newtonian assumptions. 2. E equals mc squared. Energy equals mass times the speed of light squared, revealing the unity between energy and matter. 3. Photoelectric effect. Demonstrated that light behaves as particles, quanta. This work earned him the Nobel Prize. 4. Brownian motion. Provided empirical proof of the existence of atoms. Einstein later expanded his work to general relativity, predicting gravitational waves, describing black holes, and reshaping cosmology. Today, GPS systems, lasers, and many communication and medical technologies depend on Einstein's theories. 3. Newton versus Einstein. Complementary, not competitive. Trying to decide which genius eclipsed the other misses the deeper truth. Newton and Einstein did not stand on the same battlefield. Instead, they built 2 different levels of the same cathedral of knowledge. Newton explained the world of ordinary speeds, masses, and distances. His physics describes falling apples, orbital planets, and the predictable behavior of matter. Einstein explained the universe at extreme speeds and enormous gravitational forces. His physics describes the bending of space-time, the behavior of light, and the structure of the cosmos. Where Newton mapped the stable floor of classical mechanics, Einstein opened the doors to the strange corridors of modern physics. Without Newton, the scientific world would lack its foundations. Without Einstein, it would lack its horizons. Conclusion. Both Isaac Newton and Albert Einstein reshaped human understanding in ways that continue to influence science, technology, and philosophy. Their discoveries still guide satellites, telescopes, computers, hospitals, and every branch of scientific research. Rather than asking who was greater, it is more meaningful to see them as two luminous minds illuminating different dimensions of the same universe. Their legacies remind us that knowledge grows not in a straight line, but through the daring questions and disciplined imagination of those who refuse to stop thinking. 아래는 긴 내용을 주제별 소제목으로 나누고 핵심만 간결하게 정리한 구조적 노트입니다. 마치 복잡한 숲을 한눈에 볼 수 있도록 길을 잘 닦아놓은 지도처럼 구성했습니다. 필요하면 PPT용으로도 재구성해 드릴 수 있습니다. 1. 양자란 무엇인가? 양량과 입스의 합성 측정 가능한 속도, 온도 같은 물리량은 과거에는 연속적이라고 생각했다. 하지만 미시 세계로 들어가면 값이 끊어져 있고 불연속적으로 띄어있는 형태로 나타난다. 이 불연속적 단위를 양자라고 부른다. 2. 연속성과 불연속성의 충돌. 큰 세계에서는 연속적으로 보이지만 원자 전자 수준에선 1, 2, 3처럼 단계적 값으로 존재한다. 이것이 고전역학과 양자역학의 근본적인 차이다. 3. 1927년 솔베이 회의. 역사상 가장 위대한 사진의 이유. 29명 중 17명이 노벨상 수상자. 닐스 보어, 하이젠베르크, 슈레딩거, 드브로이 등 양자역학의 주역 총집합. 코펜하겐 해석이 본격적으로 제시된 회의. 코펜하겐 해석. 미시 세계는 확률의 지배 측정을 시도하는 순간 대상이 교란된다. 따라서 미시 세계는 확정적이 아니라 확률적으로만 묘사될 수 있다. 신은 주사위 놀이를 하지 않는다. 아인슈타인은 자연을 확률로 이해하는 태도를 거부했다. 보어는 즉각 반박하며 논쟁은 보어의 승리로 평가되었다. 5. 슈레딩거의 문제 제기. 슈레딩거는 양자역학의 이상함을 드러내기 위해 사고실험 고양임을 제안했다. 오히려 양자역학의 본질을 잘 보여주는 대표적 사례가 되었다. 참을 6. 양자역학의 의미. 100년 동안 오류 없이 유지된 현대물리의 핵심 이론. 반도체, LED, 레이저 등 현대 전자제품의 기반이 모두 양자역학이다. 스마트폰의 작고 강력한 구조는 미시 세계에 대한 이해 덕분이다. 7. 상대성 이론의 등장. 양자역학과 함께 현대 물리학의 또 다른 기둥이 아인슈타인의 상대성 이론이다. GPS의 시간 보정 등 우리 삶에 깊이 적용되어 있다. 8. 특수 상대성 이론. 두 가지 전제. 1. 상대성 원리. 똑같은 속도로 움직이는 배 안에서는 정지나 이동을 구분할 수 없다. 물리 법칙은 관찰자의 운동 상태에 무관하게 동일하다. 2. 빛의 속력은 언제나 같다. 관측자에 따라 다르게 보이지 않는다. 에테르 문제와 마이컬슨 몰리 실험 빛이 지나가는 매질이 있을 것이라 가정했으나 실험은 에테르 없음을 확인했다. 이 실패가 오히려 특수 상대성 이론의 문을 열었고 두 과학자는 노벨상을 받았다. 시간 지연과 길이 수축. 빛의 속력이 일정하므로 시간과 거리는 서로 묶여 변화한다. 시간 지연. 빠르게 움직이는 곳의 시간은 더 느리게 흐른다. 길이 수축. 같은 상황에서 거리는 짧아진다. 우리가 느끼지 못하는 이유는 인간의 이동 속도가 너무 느리기 때문이다. 11. 일반 상대성 이론. 특수 상대성이 적용되지 않는 더 큰 우주 규모에서의 중력 설명. 중력의 새로운 정의. 뉴턴. 물체가 서로 끌어당기는 힘. 아인슈타인 질량이 시공간을 휘게 만들고 물체는 휘어진 시공간을 따라간다. 스타킹 비유. 큰 물체는 시공간을 깊게 휘게 하고 작은 물체는 그 흐름을 따라 운동한다. 12. 빛의 굴절과 블랙홀 빛은 질량이 없지만 시공간이 휘면 그 경로를 따라 움직이므로 휘는 것처럼 보인다. 에딩턴의 관측이 이를 증명했다. 시공간이 극단적으로 휘어진 곳이 블랙홀이다. 시간이 거의 멈추다시피 흐른다. 13. 왜 우리는 뉴턴 역학을 계속 배우는가? 지구 규모에서는 뉴턴의 법칙이 충분히 정확하다. 일반 상대성을 처음부터 배우면 지나치게 복잡하므로 실제 교육에서는 뉴턴 역학을 사용한다. This is one of the most iconic images in the entire history of physics. I will explain it without identifying any specific individuals in the photo, while still giving you a clear and professional English description suitable for lecture use. The most important photograph in physics. The photograph you are looking at is widely regarded as the most important group photo in the history of modern physics. It was taken during the 5th Solvay Conference, held in 1927 in Brussels. The Solvay conferences were elite gatherings that brought together the greatest minds working on the deepest questions in physics. This particular conference is famous because it occurred at the very moment when classical physics was giving way to the new world of quantum mechanics. The group assembled here represented the full spectrum of theoretical breakthroughs happening at the time. Among the 29 participants, 17 later became Nobel Prize laureates, a remarkable concentration of scientific achievement that has never been repeated. The discussions at this conference shaped the foundations of quantum theory, especially debates over determinism, probability, and the structure of the atom. The 5th Solvay Conference is therefore remembered not only for the brilliance of its participants, but also for the turning point it represented: the transition from the predictable, deterministic world of classical mechanics to the probabilistic, uncertain world revealed by quantum physics. The photograph endures as a symbol of scientific revolution, intellectual courage, and collaboration at the highest level. How might I connect the themes of Below is an English manuscript written in a formal, academic essay style, yet clear and readable, suitable for a lecture or presentation. The theme is predictability innate through the lenses of classical mechanics and quantum mechanics. Predictability in nature. Classical mechanics and quantum mechanics. Humanity has long sought to understand the rhythms of nature. For centuries, scholars believed that the world operated like a well-crafted timepiece, orderly, predictable, and governed by universal laws. With the rise of classical mechanics, this confidence in predictability reached its peak. Yet in the 20th century, quantum mechanics emerged and revealed a world far more subtle, where probabilities replaced certainties and microscopic particles refused to behave like miniature planets. The dialogue between these two frameworks exposes a profound question: is nature ultimately predictable? This essay explores that question through the contrasting perspectives of classical and quantum physicists and considers how their ideas reshape our understanding of natural order. 1. Classical mechanics. The confidence of determinism. Classical mechanics, developed primarily by Isaac Newton and later refined by Pierre-Simon Laplace, established the belief that the universe is governed by deterministic laws. Newton demonstrated that the same mathematical principles explain falling apples, flowing rivers, and orbiting planets. Nature, in his framework, behaves with strict consistency. Every motion follows a clear cause, and every cause produces a calculable effect. Laplace extended this vision to its philosophical extreme. He imagined a hypothetical intelligence, often called Laplace's demon, that knows the exact position and momentum of every particle in the universe. With this information, it could compute the entire past and future with perfect accuracy. In this worldview, nature is fully predictable. Uncertainty is not a fundamental feature of the world, but a limitation of human knowledge. Classical mechanics therefore portrays nature as a system of interlocking gears, elegant, stable, and ultimately transparent to rational calculation. 2. Quantum mechanics, the emergence of probabilistic order. At the dawn